It is the total number of protons as well as neutrons. Totally it is a nucleon. So this is the one which corresponds to the mass of the nucleus. E is equal to energy mc square. So E is equal to mc square is the equivalent, that is the equation for mass energy equivalence. Original atoms are there, it starts disintegrating at certain interval of time. So half of it is called as a half-life. Energy mass conversion or mass energy conversion, that conversion concept is called as mass energy equivalence, where the energy is conserved as a mass. Hello everyone, I am Vrinda, welcoming you all to chapter 13, that is nuclei. So in today's class, let us just learn much more about, we have already studied atoms, and atoms consist of a nucleus, and depth of the nucleus let us study in this chapter. So there are concepts called as isotopes, isobars, isotones. Before that, let us just check how the nuclei, that is, can be symbolized. X as well as A, and you have Z, where A turns out to be a mass number and Z turns out to be an atomic number, which corresponds to proton number, and this mass number corresponds to the nucleus. It is the total number of protons as well as neutrons. Totally it is a nucleon. So this is the one which corresponds to the mass of the nucleus. With the help of this, we have a concept called as isotopes, isobars, isotones. With respect to isotopes, it is that it has got same atomic number, but the mass number is the one which changes. So we have, for example, 1H1 hydrogen isotopes, 1H3, it is deuterium, tritium as well as hydrogen. So this is an example for isotones. When it comes to isobars, again we have A as well as Z. This is how exactly the nuclei is termed. In case of isobars, you have same mass number, but the atomic number is the one which changes. So for this, we will have an example of, we have 1H3 as well as helium. So this is an example for isobars. When it comes to isotone, here we have the same component, but the thing is, there is same number of neutrons in a nuclei. And how exactly you can check out the neutrons, how you can tell that there is the same number of neutrons? That is by A minus Z is equal to N. This is the neutron symbol. From the mass, total mass number, you are deleting only the number of proton, which gives you the neutrons, and neutrons are the one which is neutral in nature. So that is how exactly you can take out the value of a neutron. So these are all about your isotones, isobar as well as isotones. Next is, when you're going to size of the nucleus, you know that the volume of the nucleus is equal to 4 by 3 pi r cube, wherein the size of the nucleus turns out to be, you have volume is directly proportional to the mass number. So volume is 4 by 3 pi r cube is equal to r naught times that of A. So just keep r cube is equal to r naught that times of A. So we have r is equal to r naught into A 1 by 3. So this is the radius, that is the size of the nucleus. For the smallest atom, that is a hydrogen atom, if you consider, you have 1.3 Fermi. This is the least one, and for the highest it is 8 Fermi. Next we are going on to nuclear mass and density. So how do you calculate a nuclear density? So it is nuclear mass by nuclear volume. So nuclear density is nuclear mass by nuclear volume. So nuclear mass is A into Mn, because this is a mass number which corresponds to the mass of the nucleon. Nuclear volume is 4 by 3 pi r cube. So this holds good for the nuclear volume. So now R is nothing but, since R is nothing but R naught of A 1 by 3, on calculating A Mn, and this is 3 because 3 goes up, divided by 4 pi r naught a 1 by 3 of the whole 3. So 3 cancels. So we have 3a mn divided by 4 pi r naught cube and a cancels with a. So we have nuclear density is given as 3 times mn divided by 4 pi r naught cube. So this is the equation in order to tackle with the nuclear density. Next we have mass energy equivalence. Mass and energy equivalence means we get E is equal to energy mc square. So E is equal to mc square is the equivalent, that is the equation for mass energy equivalence, which is applicable in terms of pair annihilation. Next is pair production as well as nuclear fission. So pair annihilation means annihilating. It is sticking onto each other. That means to say that there is a positron, there is an electron. Both of them interfere or both of them come to each other with the release of great energy. Mass is converted to energy, that is called as pair annihilation. And pair production means you have a positron and you have an electron. So there is a gamma ray photons which comes and hits a heavy nucleus for the production of electron as well as its antiparticle. That means to say that the energy is converted to mass. That means to say there is a pair production here. Mass is converted to energy. And finally fission. Fission means a heavy nucleus is split up into finer components wherein the energy is released. Okay, that means to say that due to certain set of energy, there is a few particles which are divided. So again, it is energy to mass conversion. So energy mass conversion or mass energy conversion, that conversion concept is called as mass energy equivalence, where the energy is conserved as a mass. Okay, so all these components comes under this mass energy equivalence relation. And next we are going to nuclear binding energy. So what is binding energy of a nucleons? It's a minimum energy required by the nucleus to split up into its constituent nucleus is called as the binding energy. And the definition is very much important, wherein you will have a binding energy curve to which you have certain set of graphical representations. And next we have a nuclear force. So what is a nuclear force? Nuclear force is also called as, it is a short range force, one of the main fundamental force in nature. It is charge independent. It is spin dependent force. So this is how exactly the nuclear force turns out to be. These are the nuclear force properties. Okay, so it is one of the fundamental force in nature out of gravitational force, electromagnetic force, strong nuclear force as well as weak nuclear force, out of which the normal nuclear force is the one which are having these set of concepts. And next we have law of radioactive decay, which means to say the rate of disintegration of a radioactive substance at any instant of time is directly proportional to the number of atoms present in that substance in that interval of time. That is the rate of disintegration, that means dN divided by at certain interval of time is directly proportional to number of atoms of that substance present in that instant of time, that is dN divided by dt is proportional to n. When you remove this proportionality constant, we have dN divided by dt is equal to minus lambda into n, where minus lambda is nothing but the minus negative sign, which means to say that the atoms are decreasing at certain interval of time, where lambda is known as decay constant. So for which we have dN divided by n is equal to minus lambda into dt, So for this set of equation on integrating it, we have integration of dn divided by n is equal to integration minus lambda into dt. So integral of this log to the base en is equal to minus lambda out. So integration of dt is nothing but t plus c. Case, that is if n is equal to n naught at t is equal to initial time, at time is 0, then the equation turns out to be log e n naught is equal to lambda of 0 plus c. So instead of c, you have this equation. So you can just rewrite to this equation as log e n is equal to minus lambda t plus log e n naught. Take this towards the other side. So log base e n minus log e n naught is equal to minus lambda t. So we have this equation. On equating this equation further, we will have log to the base n by n naught is equal to minus lambda t. Take the log towards other side. It turns out to be exponential n minus n naught is equal to exponential of minus lambda t, or you can even write it as n is equal to n naught e minus lambda t. So this is a set of equation in order to determine the law of radioactive decay law. So this equation tells that if you just have a graphical representation with respect to T as well as number of atoms present over there, there is a decrease in the radioactivity. That is, as the time increases, it starts disintegrating and it is given in terms of exponential term. Suppose if lambda, suppose you have your lambda is equal to 1 by t, then the equation turns out to be n by n naught is equal to exponential of minus 1 by t into t, t cancel. So n divided by n naught is equal to exponential of minus 1 or 1 by e. This is the final set of equation if the condition this arises. Otherwise, you can wind it up here itself for the law of radioactivity active decay. Next, you have lambda is equal to 1 by t, that is the known as decay constant. So next you have your half-life. In half-life, the time during which the half of the original atom disintegrates is called as half-life. Original atoms are there, it starts disintegrating at certain interval of time. So half of it is called as a half-life. In order to derive it, we have a set of equation known as n is equal to n naught exponential of minus lambda t. Suppose according to that equation, that is the time during which half of the original atom disintegrates, half we are considering it as n naught by 2. On application on the same, we have n naught divided by 2 is equal to n naught e minus lambda t. N naught divided by n is equal to 2 times exponential of lambda t. N naught cancels. Taking this exponential, we have, taking it to the other side, we have e lambda t is equal to 2. So on application of log, you have lambda t is equal to log to the base e and 2. If t is considered to be t, then lambda capital T is equal to log to the base e and 2. Time is equal to log to the base e into 2 divided by lambda, or you can even write this as, in order to take this to log to the base 10, t is equal to 2.303 into log 10 of 2 divided by lambda, or else even you can call it as 0.6693 divided by lambda. So this holds good for the half-life of the nuclei disintegration. In today's class, we have dealt with the chapter nuclei. Let us all meet in our next upcoming session. Until then, have a good day. Thank you.